All right, and today we're gonna actually shift from dealing, solving right triangles and I guess dealing with solving some trig equations, and we're gonna take a look at solving some oblique triangles. So I'm gonna just go into the lecture notes section, and this is chapter 10, but here again, this was taken from a different textbook. There are also a couple of videos you may or may not want to take a look at. Here's a video for the law of sines, which we're going to discuss today. And then there's another video for the law of cosines. But I'm going to bring up section 10.1, and it deals with the law of sines. But before we begin, I'm going to bring up OneNote. And I'm also going to bring up the formula sheet. All right, and I'm going to bring up the all exam formula sheet. And what we basically did in the last chapter or last chapters, we kind of went through the first part or of the formula sheet. You notice at the very bottom of the formula sheet, there are formulas for the law of sines and the law of cosines. And this is what we're going to be dealing with in the next module. And here's where the law of sines and cosines come in. So as far as the problems are concerned, okay, we're not going to use any of the problems prior to the law of sines and the law of cosines. There's two types of triangles. There are right triangles, right? And in a right triangle, the right triangle must contain a right angle, right? So if that triangle contains a right angle, it's considered to be a right triangle. And if you're dealing with the right triangle, the Pythagorean theorem, right, the c squared equals the a squared plus b squared, right, that can be used. The 6 trig functions can be used. All the other formulas that we've talked about thus far would be pertinent. However, when we talk about oblique triangles, right, for oblique triangles, there are no right angles. And there's actually two different types of oblique triangles. We have what are called obtuse triangles, right? And in an obtuse triangle, at least one of the angles must be obtuse. So keep in mind that an obtuse triangle or an obtuse angle is an angle that's greater than 90 but less than 180. All right, so looking at this particular triangle, this would be an obtuse triangle, and this would actually be our obtuse angle. We also have what are called acute triangles, right? So in an acute triangle, all of the angles are less than 90 degrees. Notice that in these two types of triangles, there are no right angles. So the Pythagorean theorem and all of the formulas that we've used thus far, they don't count towards oblique triangles. When we talk about oblique triangles, we solve them by using the law of sines and or the law of cosines. Okay, so this is a shift in what we've been doing. However, no matter what triangle that you're dealing with, this is a fact that's true for any triangle, whether it's a right triangle or an oblique triangle. And it's called the sum rule. And it says that the sum of the interior angles of any triangle must equal to 180 degrees, right? Which means that if we're given two angles, we can always find the third angle based on the fact that there are 180 degrees within the sum of the interior angles of any triangle, right? So you're going to see this sum rule used in the problems that we're dealing with today. All right, so with that being said, I'm going to go back to the lecture notes. And here we have the law of sines. And the law of sines read, in any triangle ABC with sides A, B, and C, we have that side length A divided by the sine of angle A is equal to side length B divided by the sine of angle B, and that's equal to side length C divided by the sine of angle C. Sometimes you may see the formula written in an alternative form, right? You can have your angle measures on top and your side lengths on the bottom. There is no right or wrong on how you set up your proportions. You just want to be consistent in that if you're using the side lengths in the top, you just want to make sure that the side lengths are in the top, or if you're using the side lengths in the bottom, just be consistent and use the side lengths in the bottom. Now, as far as the law of sines is concerned, we won't use all three angles. We will use two angles, right? We're basically going to set up a proportion, and a proportion is nothing more than two angles that are a proportion is two fractions that are equal to each other. And we solve a proportion by using the cross product property. So notice that when we set up our proportions, there must be only one unknown. If we have more than one unknown, we can't actually solve. All right, so here's an example, or here's the cross product property, I should say. So the cross product property says if we have a proportion, okay, A over B is equal to C over D. So just keep in mind that a proportion is two fractions that are set equal. Then we can actually cross multiply. We can multiply 8 times D, and we can set that equal to B times C. All right, so when we set up our proportion, there must be only one unknown. All right, so we're going to take a look at an example. And when I flip my screen over, I close down all of my windows. So let's see. Give me 1 second to log in. All right, and we're going to take a look at problem number 1. All right, and it says assume that alpha is opposite of side A, beta is opposite side B, and gamma is opposite side C. We're asked to solve the triangle and round all answers to one decimal place if necessary. Okay. So we're given that alpha is 60 degrees, gamma is 25 degrees. We're also given that A is equal to 15, right? So that's side length A. Okay, before we go any further, I just want to I just went to Google and I typed in Greek alphabet. And I'm just going to bring up this document. All right, so unlike algebra, right, in algebra we dealt with variables are unknown. or unknowns, and in algebra, the variables were represented as letters, right? A, B, C, or X, Y, Z. However, in trig, our variables or our unknown quantities are expressed as letters of the Greek alphabet, right? So here's some of the Greek alphabets that we're going to encounter in this course. Okay, you're going to see alpha often, you're going to see beta often, and you're actually going to see gamma often. All right, so we have alpha, beta, and gamma. If you are looking at a problem and you're unsure of which Greek alphabet that they're using, you can just do a quick Google search. But the variables we're going to use are alpha, beta, and gamma. Right, so give me 1 second and I'm going to write these things down. All right, so this is 4.1, number 1. So I'm going to simply draw out a triangle. So this is not drawn to scale. So from what we were given that alpha is 60 degrees. And from the given information, it says that alpha is opposite side alpha. And we're also given that alpha is 15. So this is capital alpha here, and this lowercase alpha. We're also given that gamma is 25 degrees. And from the given information, it says that C is opposite gamma. And last, we have beta, and opposite angle beta, we have B. All right, so this was all of our given information. All right, so now we want to set up a law of sines. Okay, so let's take a look at what we're given. So we're given angle alpha. We're also given side alpha, right? So we're given an angle and we're given a side. I'm not given beta and I'm not given side B, but I'm given gamma and I'm given gamma as 25 degrees, but I'm not given C, which is the opposite of gamma. All right. I can actually set up a law of sines function to find side C. Right. So when I set up my proportion, C would be the only unknown. So keep in mind, when we set up our proportion, we can put the angle measures on top, we can put the angle measures on the bottom, but we have to make sure that we remain consistent. All right, so for my purposes, I'm going to put the angle measures in the numerator. So I'm going to write this out as the sine of 60 degrees, right, divided by 15. That's equal to the sine of 25 degrees divided by C. All right, so keep in mind from our law of cosines formula, I'm just going to go back for a second. Right, as long as we put the angle, the sine of the angle divided by the corresponding side length, right, we're maintaining the correct property for using the law of sines. All right, so looking at the setup, you can take the sine of angle A, divided that by side length A. So keep in mind that A, side length A, is opposite angle A. And we can set that equal to another angle divided by the side opposite that angle. All right, so that's what we have here. We have the sine of 60 degrees divided by 15, right? Because the 15 side length is opposite angle 60. And we can also set up the sine of 25 degrees divided by C. Okay, so now that we have our proportion with only one unknown, the next thing I'm going to do is use a cross product property and multiply. Okay, I'm going to cross multiply. So C times the sine of 60 is C times the sine of 60 degrees. That's equal to 15 times the sine of 25 degrees. Now I'm going to solve for side length C. So I'm going to divide both sides by the sine of 60. So C is equal to 15 times the sine of 25 degrees divided by the sine of 60 degrees. And now I'm going to evaluate using the calculator. All right, now since we are using degree measures, I have to make sure that my calculator is in degree mode. Okay, often when you're working with the calculator, you can be doing your problems, exactly right, but if your calculator is in the wrong mode, you will get the wrong solution. So since I'm inputting degree measures, I want to make sure my calculator is set to degree mode. Now that we have the proper mode, I'm going to enter this in as 15 times the sine of 25 degrees, making sure you close off your argument for sine, divided by the sine of 60 degrees. And if we round to one decimal place, we have 7.3. All right, so we found side length C. Okay. All right, so now we need to find angle beta or side length beta. Now, in order to set up another sine function, right, we must either know the angle measure or we must know the side length opposite that angle. And here for B, for angle beta and side length B, we don't know either one. But we could use the sum formula to find angle beta. So I'm going to find beta here. So angle beta, that equals to 180 degrees minus the 60-degree angle plus the 25-degree angle, right? So notice that this is the sum rule. It states that all three angle measures must equal to 180 degrees. So if we were to add $60 and $25, we get $85. And if we were to subtract, angle beta should be 95 degrees. All right, so we have beta as 95 degrees. All right, and this would allow us to set up a law of sines proportion to find side length B. right? So here we're going to find B. Now, this is what I'll usually do in order to avoid rounding error. So notice that for when we found side length C, we use 7.3, but we use it a rounded value. I normally will use the given values. So for example, they gave us the 60-degree angle and they gave us the side length opposite the 60-degree angle. So when I actually find side B, I'm going to set up my log sines proportion as the sine of 60 degrees divided by 15. That's equal to the sine of 95 degrees divided by side length B. I'm going to cross multiply, so B times the sine of 60 degrees is equal to 15 times the sine of 95 degrees. I'm going to divide both sides by the sine of 60, so B is equal to 15 times the sine of 95 degrees divided by the sine of 60 degrees. I'm going to evaluate that on the calculator. So we have 15 times the sine of 95 degrees. So make sure that you close off your argument for sine divided by the sine of 60 degrees gives us 17.3. Right, that gives us 17.3. So B is 17.3. All right, so we have solved the oblique triangle. All right, so now here's another fact. I'm just going to go back slightly. All right, so here's was one fact, right? This is called a sum rule. The sum of the interior angles of any angle must be 180 degrees. So here's another fact number 2. The smallest side or I should say the smallest side length is opposite the smallest angle and the largest side length is opposite the largest angle. All right. So it says that the smallest side length is opposite the smallest angle, and the largest side length is opposite the largest angle. All right, so let's take a look at that. So if I go back to my triangle, I see that the smallest angle is 25 degrees. Opposite the smallest angle should be the smallest side length. So 7.3 is the smallest side length. And then if I look at angle B, right, angle B is my largest angle. And if I look at side length B, it is in fact the largest side length. All right, so entering those values in, we have beta is 95, angle B is 17.3, C is side length, C is 7.3. All right, so we have 95 for angle beta, Side length B is 17.3 and side length C is 7.3. All right, I want to go back to the lecture notes for 1 second, and I want to talk about the data that's actually required for solving oblique triangles. Okay, so we have what are called the different cases. Now, the cases aren't really that important, but there's one case that you need to be mindful of, and that's case number 2. Okay, and we'll see why in just a second. So notice that case number 1, it says that, and this is the data you must have in order to solve an oblique triangle. We have side angle angle or angle side angle. We have case number 2, and case number 2 is called the ambiguous case. We have a side angle. So notice that side angle is the dirty word spelled backwards. So whenever you are given those dimensions, it can lead to more than one solution. So when I say it can lead to more than one solution, whenever you have a side angle set of measurements, you can either have a no triangle solution, you can have a one triangle solution, or you could have a two triangle solution. Okay, but we'll talk more about case number 2 in the next section. We have case number 3, which is the side angle side. So if you're given two sides and an included angle between the sides, that's enough information to solve using an oblique triangle. And then case number 4 is all three sides. So I'm actually going to sketch these things out. So notice we have that case number 1, we have a side angle angle, right? So what does that actually mean? Right, well, if I have a triangle, I would be given the measurements of one side, I would be given the measurements of another angle, and I would also be given the measurements of an angle that's included in between the side and the angle measure. Now, one thing, you'll see these little tick marks going around the triangles that I tend to draw, and here's what these mean. Here's what the tick marks mean. Okay, notice I have one tick mark here, so that just notice that this denotes a side length. Notice I have an angle measure that has one tick mark and another angle measure with two tick marks. The tick marks allude to the fact that the angle measures are not the same, right? So keep in mind, if you're given a side angle set of measurements, you could use the law of cosines, right? Because in the law of cosines, I could set up a side, I could set up an angle measure, the sine of this angle divided by this side length, and I can set that to the sine of this angle measure divided by the side opposite to it, right? And we can use the law of cosines to find. You can also have an angle side angle set of measurements, right? So what does that look like? So for an angle side angle set of measurements, I'm given an angle measure, I'm given another angle measure, and I'm given the side that's included between those two angle measures. And you could also use the law of sines to solve this triangle, right? Because here we could use the sum rule, we could find this angle, right? We can use this angle and the side opposite that angle, and then we can set up the sine for any one of the other angles and solve for our missing side length. All right, so this is case number 1, side angle angle and angle side angle. Case number 2 is the ambiguous case, the side-side angle set of measurements. So this is known as the ambiguous case because it has three solutions. There can be a no triangle solution, there could be a one triangle solution, or there could be a two triangle solution. Right? So for a side-side angle set of measurements, we're given a side, we're given an angle measure, and then we're given a side length in between the side and the angle given. So notice for this setup, the side-side angle, we in fact could not use the law of cosines because we wouldn't have enough information to set up a proportion. However, we could use the law of cosines, which is what we're going to talk about in the next section. Next, we have case number 3, which is side angle side. Right, so for side angle side, you're given a side length, you're given another side length, and you're given the measure of the angle included between those two. Right, so here again, you can solve this triangle by using the law of cosines. Right, there's not enough information to use the law of sines, right, because there's too many unknowns, but we can use the law of cosine. And then in case number 4, we have side, side, side. Right, so if you're given all three side lengths, you could find all of the angle measures by using the law of cosines. Right, so these are the 4 cases, okay, with the information that's used in order to find or to solve an oblique triangle. Now I want to look at case number 3 for just a second, the side-side angle setup. Okay. And the side-side angle setup is if you're used to find area. So right underneath, I'm going to write area formulas. Okay. So normally, if you were finding the area of a triangle, all right, so this is from classic geometry. All right, so let's just say we have this triangle. So we're going to say that this is, the height is 10. The base is, let's say, 4. So we have the area is 1/2 the base times the height. Right, so the base is 10, the area is 4. So if we were to plug this in, we have 1/2 of 10 times 4, which would be 20. And since we have area, that would be square inches, right? So let's say we had an example that looks like this. So again, the height is 10 inches, and we're going to say the base is 4 inches. So again, the area is 1/2 the base times the height. So the height is 10, the base is 4. So again, we would get 20, right? But notice, in order to use the formulas for classical geometry, you must know the height, right? Because in that formula is 1/2 the base times the height. So now if you're not given the height, here are some alternative formulas in order to find the area. So I'm going to just draw out this triangle. So we have, this is angle A, this is angle B, this is angle C. And here I'm just using standard labeling, right? Which means that the angle measures are capital letters, the side lengths are lowercase letters. So the side that's opposite angle A is side length A. The side that's opposite angle B is side length B. And the side that's opposite angle C is side length C. Right? So here are the formulas. So the area could equal to 1/2 A times B times the sine of angle C. So notice I'm not given a height, but if I'm given a side angle set of measurements, I could find the area. The area is also equal to 1/2 B times C times the sine of A. So notice again, that is a side angle side. Oops. So notice I'm giving B, C, and A. Sorry, I'm giving a side angle side set of measurements. I can find the area. And the third formula is 1/2 A times C times the sine of B. Right, so here again, if I'm given a side angle side set of measurements, I can find the area. All right, so let's take a look at an example. Okay, I believe the very last problem, number 7, it asks us to find the area of the triangle with the given measurements. All right, we're given side A, side C, and we're given the measure of angle B, right? And we're asked to find the area. All right, so here's an example. We're going to find the area. So this is A, B, C. We're given that A is equal to 4, C is equal to 4, and beta is equal to 30. All right, so I'm going to give you a couple of minutes or so. I would like for you to find the area, and then we're going to return with the solution. All right, so taking a look at the solution, we're going to use a formula that the area is equal to 1/2 A times C times the sine of beta. So A equal to 4, C equal to 4, and beta equals to 30. So that's 1/2 times 4 times 4 times the sine of 30. So we're going to put that into the calculator. So I'm going to put in 1/2 or 0.5 times 4 times 4 times the sine of 30. And we have 4. So the area for this triangle should be 4 square units. All right. And then lastly, I would like for you to do problem number 4. Right, it says find the length of side x, round to the nearest 10th. So I'll give you all 5 minutes or so. I would like for you to do number 4, and then we're going to return with the solution. All right, let's take a look at the solutions. All right, so here we're asked to find angle X. All right, so the first thing we're going to do in order to find angle X is we don't quite have enough information to set up a law of sines function. Keep in mind that we can't use Pythagorean theorem or anything. So what we're going to do first is we're going to find this missing angle measure. And we're going to use the sum formula. So that missing angle measure, I'm just going to put the symbol for angle. That equals to 180 degrees minus the sum of the other 2 degrees. Right? So if we were to add 75 and 45, we would get 120. And 180 degrees minus 120 degrees is 60 degrees. Right? So we have the missing angle measure of 60 degrees. So now we can find we can find side length X by setting up a law of sines function. Right. So I can actually use the 45 degrees is opposite angle X. So I have the sine of 45 degrees divided by X. That's equal to the sine of 60 degrees divided by 14. Right, I can cross multiply, so we have 14 times the sine of 45 degrees is equal to X times the sine of 60 degrees. I can solve for X by dividing both sides by the sine of 60. I'm just kind of flipping it around here. So I have 14 times the sine of 45 degrees divided by the sine of 60 degrees. So if we were to put this into the calculator, 14 times the sine of 45 degrees divided by the sine of 60 degrees. And we get 11.43. So that'll be 11.4. All right. All right. So I believe we're going to stop here for today. I'm going to stop the recording.